Hi everyone. Just addressing your feedback from today's lecture. Let's see here. Do the energies of each particle add up every time they collide? I wouldn't say they add up. I would say that their energy changes as they get closer to each other or further apart from each other. We think of energy, especially. I think I didn't quite describe this as accurately as I could have. So I just said energy was my chart here, and to be more specific, I should have said potential energy. So potential energy is an energy at position, so it's their energy that depends on how close they are, or the arrangement of the atoms in each of the molecules. So I would say that the energy of the molecules increases as they come close to each other and collide, and then it decreases as they, or potentially, yeah, and then it decreases as they separate from each other. Does the temperature increase also increase collision frequency, and that's why the rate increases? It does both. So increasing the temperature increases the fraction of molecules that will have the necessary activation energy to exceed the activation barrier, but it also does increase the collision frequency. And that does that in a fairly, I won't say in an unpredictable way, but in a difficult to predict way. And so at this level, we kind of ignore that. But that is something that also increases the rate of the reaction, which is the fact that as you increase the temperature, the particles move more quickly, and so they collide with each other more frequently. Are your exam questions similar to the quiz? They will be somewhat similar to the quiz, and they will be a little bit of similarity with the homework. And I also have a tendency to ask just straight up definition style questions. That I would like people to be able to give me a definition of things like activation and energy, and also be able to find it mathematically. I'm using that as an example. I'm not saying I will ask those specific questions. But yeah, this is a frequent thing that can happen in general chemistry. Is you can calculate something, but you don't necessarily need to know what the thing is in order to calculate it. And I want to make sure people also understand what it is they're calculating, or what it is they're doing calculations with. So if you would like some examples of what my exam questions look like, please check on the Brightspace website. I've posted my midterms and final exam from last semester to give you an example of what my questions look like. Yeah, they are kind of similar to the homework, and they are going to be a little similar to the quizzes as well. The quizzes, I have to sort of change the format a little bit just because there's only 10 minutes for the quiz, so I can't really ask a deep, insightful question. Or at least not that many deep, insightful questions, or any complex calculations, simply because people just don't have time to do it. But you'll have 5 times longer for the midterm, so there's that. I got lost in figuring out what exactly we were out to learn today. Okay, that's actually a legitimate, not legitimate, they're all legitimate comments. But that's an important criticism that I will take to heart. I used to do this, I was doing this more last semester. I'll start doing it again, where I would basically give the title, I'd give a title for the lecture, and basically say, okay, this is what we're going to discuss today. I sometimes, I have a tendency to, or a desire to not want to do that, because I normally want to build up to something. And I don't want to spoil the surprise. That's me trying to make a big performance out of it. Maybe I shouldn't do that. Maybe I will try going back to framing the lecture in the beginning. And this comment was there was another comment. Sometimes writing on all the boards and then jumping back and forth is confusing. I can see definitely the jumping back and forth being confusing. But the reason why I like to jump back and forth is because I write everything is on the board. When everything is on the board, it's easier for me to refer back to something without, if I was doing it in a PowerPoint, I have to go back through slides, and then that disrupts everything. If everything is up on the board, I just walk back over to where the board is. And sometimes that's because, okay, I am trying to connect things I started discussing the lecture with, try to loop back and explain, okay, this was supposed to be indicative of something that we're going to discuss later on, and I can tie it back there. So I do recognize that can be confusing, but I am also of the opinion that I will try to not jump back and forth as much if I can avoid it. So I do take your criticism to heart. If the collisions occur at a higher rate in smaller spaces, does that mean that rate is volume dependent? I would say it's volume dependent only in the sense that it's concentration dependent. Most specifically, rate depends on concentration. Concentration depends on volume. Molarity is moles per unit volume. So in that sense, it's volume dependent. More formally, it's concentration dependent. So I would say it's tangentially volume dependent. How do you determine Z and P in this equation? So Z was the collision frequency, P was the orientation factor, and then I had this energy factor here, which was the fraction of the particles that will have the appropriate activation energy. So this was the collision factor, or rather the collision frequency, and this was the orientation factor. And the short answer is you can't easily determine them. You can't. They're intimately tied together, at least in usual experimental data. It's more so we just kind of want to introduce them. I wanted to introduce them as a concept, just to know, okay, it depends on how frequently things collide, but only some of those collisions will have the right orientation. So how do you determine them? You can do like a molecular analysis, like you can actually take molecular models and figure out, okay, the molecule needs to come in from a certain angle. So there's only a certain, the angles go 360 degrees in one direction, 180 degrees in the other direction. So you kind of limit, you can create like a cone around which, I'll give you an example. I won't draw that out because I don't know how to draw it. You can create like a certain region of space. Okay, if the particles collide from between this angle and this angle, that's a certain fraction. So you can kind of you can kind of determine it using molecular modeling. But experimentally, you can't really determine it. One thing you can determine, though, is their product. Their product is what I call just the collision factor, A. So one thing you can do, and I'm going to talk about this more in detail on Friday, but I'll give you a little preview here. If I take the natural log of this whole expression, I'll get natural log of K, natural log of A, and then I'll have e to the negative EA over RT. And then what I can then do is I can make a plot. I can do a reaction at various temperatures, measure the rate constant at those different temperatures, and then if I plot natural log of the rate constant versus 1 over temperature, then I should get a straight line. And you do get a straight line. The slope of that line should be equal to negative EA over the gas constant, and then the y-intercept is equal to natural log of the collision factor. So you can get the collision factor, and again, the collision factor is the product of the collision frequency and the orientation factor. So you can't get either of them. You can't get both of them, or rather, you can't distinguish between the two of them. But you can't find each of them individually. But you can find their product by measuring the reaction rate versus temperature, or inverse temperature. Is the largest that EA over RT can be 1? Okay, so the largest that EA RT, so your question is specifically about EA over RT. Is the largest that can be 1? No, it can definitely be larger than 1. I mean, it's just a regular fraction, Activation energy can be in the kilojoules per mole. Temperature can be, any value. So, or not any value, any positive value. So this can take any value. What does have a maximum value, though, of 1 is e to the minus EA over RT. This has a maximum value of 1, and that's when the temperature is much, much larger than the activation energy. This exponential term here, which we call a Boltzmann factor, that has a maximum value of 1, basically mean you have 100% probability that the particle will have enough energy to go over the activation barrier. The minimum value it can have is 0, and that's when the temperature is much, much less than the activation energy. And I guess I'm noting right here, really, if I want it to be more accurate in what I was saying, what I should really say is gas constant times T, gas constant times T, because temperature has units of Kelvin and activation energy has units of joules or joules per mole. So to make those units match up, technically you need to multiply by RT. Basically, yeah, this factor can either be infinitely large or it's a fraction. It can either have a value of infinity when activation energy is really high and temperature is really low, or it can have a value of 0 when the temperature is really high or the activation energy is very low. And then I'm taking something and I'm either taking an exponential e to the 0, that corresponds to 1, or I have e to the negative infinity and that corresponds to 0. That I either have 100% of them will have enough energy or 0% of them will have enough energy to go over the activation barrier. Okay, so clarifying that, I got a second question here. If the activation energy is greater than temperature, does that mean that K equals 0? So if activation energy is greater than temperature, then K equals 0. I will say your question was specifically if it's greater than, like just a single greater than. I will say if activation energy is much, much, much larger than RT, so that's why I'm going to put the double greater than symbols there, then yeah, the rate constant will go to 0. If the activation barrier is too high, none of the particles will be able to get over it, and so none of the collisions will be successful and the reaction won't happen, so the rate drops to 0. So that I will say is true. Then you had a second question, which is if the temperature is larger than the activation energy, so I'll say yes to that, then K equals A, and I will say yes to that as well. But again, it's specifically if the temperature is much, much higher than activation energy. If it's only a little bit higher than it, it'll be somewhere in between 0 and 1. The Boltzmann factor will be between 0 and 1. So the rate constant will be between 0 and A. But yeah, in the extreme case, when the temperature is much, much higher than the activation energy barrier, then the rate constant goes to A, equals A. So that actually, there was another question here clarifying that. Does that mean that the rate constant always stays between 1 and 0? No, the rate constant, K, can take any positive value. It goes from 0 to A. The Boltzmann factor, the energy factor here, that goes from 0 to 1. So this ranges from 0 to 1. And then I'm multiplying that by A, which means that K goes from 0 to A, anywhere in that range. In your energy diagram plot, where does this energy, where does that energy come from? It can come from any number of sources. I mean, the energy is interconvertible. You can convert energy from one source to another. It could come from a collision. So I emphasize here, this plot, this curve represents the potential energy, the energy of the particles based on their positions alone, where the atoms are arranged. They're just their positions. So if you get them really close to each other, you start trying to make more bonds than you should. That raises their energy, and then they'll drop down as they make a different set of bonds. They'll drop down as they make a different set of bonds. I guess the question is, where do they get the energy to go over that hill? That could come from a collision. A collision meaning they have a lot of kinetic energy. So again, emphasize, this represents their potential energy, the energy requirement based on where you put these molecules, their locations. The energy to go over that barrier could come from a collision. So that could just be because they have high energy, high thermal energy. It could come from a photon. There are photo-activated reactions. I'm trying to think if there are any other major examples. It could come from some other molecule that collides with them and transfers energy. There's lots of sources of where that energy could come from. Yeah, that's all I'll say. What would the diagram look like for a two-step reaction? All right, I'll tell you that a two-step reaction would have two energy barriers. A two-step reaction is a couple of reactions all in a sequence, literally a couple reactions. And again, every reaction has an activation barrier. So a two-step reaction might look something like that. Here is the first reaction. You go up in energy and you come down to some stable low point, local minimum energy, and then there's a second reaction with a second activation barrier that you need to surmount. So that's what a two-step reaction profile would look like. When can we use the Arrhenius equation? How do we use it in an actual question? So when do you use it? Well, you'd use it whenever you want to relate rates, constants, to activation energies, and to temperature. So there are tons of questions that you could come up with that in some way asks about how these three terms are related to each other. Very rarely will I actually care about the collision frequency or the collision factor. That'll either be given to you or you work with a derived form or a form of the Arrhenius equation that's been worked on, for lack of a better word, to get rid of the collision factor. And so there are times when, okay, I can measure the rate constant at various temperatures and I can calculate what the activation energy might be. So there are questions where you might want to actually use its functional form. I showed an example just here that you make a plot of it. If you assume that a real reaction should follow the Arrhenius equation. You make that assumption, and then you go and you actually do some experimentation, and then you assert, okay, because it follows the Arrhenius equation, the slope of my experimental data should have a value of the activation energy over the gas constant. And from my experimental data, I can then determine the activation energy for a reaction. So that's one way you might use it in practice. In an actual question, I might give you the rate constants at two different temperatures and ask you to determine the activation energy. And I'll do some more examples with that on Friday. So there are calculation style questions, and then there are just conceptual style questions. Does a reaction that have a low activation energy, is its rate more susceptible to temperature changes than, say, a reaction that has a large activation energy? And you can use the functional form of the Arrhenius equation to make that assertion. So how would you use it in an actual question? I will give some examples of that on Friday, is what I will say. What is A in the Arrhenius equation? Essentially, A is, so the term that's given is the collision factor. I'm using too many colors, or I'm running out of colors. And essentially it is the collision rate, and it's more specifically, it's the number of collisions per second that happen to have the right orientation. So again, the idea is for reactions to be successful, they need for reactions to occur, particles need to collide. So that's one thing, the number of collisions per second. They need to collide with the right angle, the right orientation. So that's the second thing you need to take into account. So I can lump those two together into the collision factor, just the number of collisions there are per second that happen to have the right orientation. And then you say, okay, not only do they have to have the right orientation, they also have to have enough kinetic energy when they collide. The collision needs to be violent enough or energetic enough for you to break all these bonds and to form new ones. Where did you get this? I admit, I did kind of just present that to you guys. The actual derivation of it is long, messy, and I don't remember it. I learned that in graduate school, and I don't remember it. Point being that it comes out of a branch of physics called statistical mechanics, where you use statistics of many, many particles, and you look at how their energy should be distributed most probably among a large collection of particles. And if you work through that derivation, you can get, okay, the fraction of particles that have a certain energy at a given temperature is given by this exponential term. So there's no way in heck that I was going to be able to work through that derivation. I'm going to present it to people. Now, the functional form of the Arrhenius equation actually was determined experimentally by Svante Arrhenius. He was doing this analysis. He was making measurements of rate constants versus temperature and trying to analyze that data to see if he could find any patterns. And one thing he noticed was if you took the natural log of their rate constants and plotted it versus 1 over temperature, he saw you got a straight line. And in science, generally, we're always, and especially any science where you have data analysis, we're always looking for straight lines. Straight lines seem to have meaning. So based upon the fact that he was taking natural log and 1 over temperature, he asserted there had to be some type of linear equation like this, and he sort of backed out a possible equation to describe it. And so he called the slope of that line the activation energy. So where did I get it? Chemists got it experimentally by analyzing data and looking for patterns. You can also derive it from first principles, but the first principles part is basically trying to figure out, yeah, I admit I'm glossing over that detail of where the actual functional form of this energy factor comes from. Can a larger activation energy be the reason a reaction is endothermic? I would say no to that. There's no necessary correlation between a high activation energy and a reaction being exo or endothermic. It seems logical. I admit it seems logical that if it takes a lot of energy to get up to the transition state, well, you need to put in a lot of energy. But that doesn't tell you anything about where the next step is. Whether a reaction is exothermic or endothermic does not depend on what happens in between. And so there's a famous, familiar statement, which is that thermodynamics, the study of thermodynamics is solely concerned with the beginning point and the starting point, the ends of a reaction, where you start with versus where you end with. This is thermodynamics. And you can predict whether a reaction is exothermic or endothermic by applying the principles of thermodynamics. That's something you can do. But thermodynamics has nothing to say about what happens in between. That falls into the branch of kinetics. So transition states, activation energies, and whatnot, those you can't really make any predictions about whether something will be exothermic or endothermic. I would say they're not correlated in any way. All right, last question here. When we have the rate constant, rate is equal to K times the concentrations of A and B, how are A and B independent of temperature? To a first order approximation, they are independent. They just are independent of temperature. More technically, especially if you're talking about molarity, and these usually are molarities, we define molarity as the number of particles per volume of solution. And the volume of a solution is somewhat temperature dependent. If you heat up a liquid or any solid, or if you heat up a gas for that matter, it does tend to expand. But to a first order approximation, if we're dealing with a if we're dealing with a reaction in solution, we're going to assume you heat it up and its volume doesn't change very much. So I can say that the molarity of the solution doesn't change much with temperature. So in that sense, I can say that those terms are temperature independent. All the temperature dependence of the rate primarily comes in at the rate constant. Okay, so that's all your questions for today. Thank you for leaving all the feedback, and I will see everybody on Friday. Have a good day.